Hello once again. We are back with another video solution to a tutorial problem in chapter 11. This time it's problem 53. Problem 53 reads, in a ballistics test, a 25-gram bullet traveling horizontally at 1200 meters per second goes through a 30 centimeter thick 350 kilogram stationary target and emerges with a speed of 900 meters per second. The target is free to slide on a smooth horizontal surface. So our first task is to draw a before and after picture of the scenario. This is a common step I really suggest doing, is just drawing a quick picture of before and after. Drawing a collision is very hard. It's very hard, but trying to draw before and after, that hopefully kind of clarifies things. So before and after. Before, we have a bullet coming in. Bullet comes in at a very fast 1200 meters per second. The mass of this bullet is very small, 0.025 kilograms, and there is some stationary target here, and that is key. It's stationary, so V equals 0, and we know that it's 350 kilograms. So that's our before picture. Our after picture has our bullet traveling through and out the other side of this target, and it's going 900 meters per second, still 0.025 kilograms, and our 350 kilogram target now is also moving with some V2F. How do we know that it's moving to the right? Well, if our bullet goes through it, just kind of by intuition alone, I don't know if I've ever seen a scenario in which something has gone through another object and that other object moves forward. It doesn't, it common sense, being on this earth for, somewhere between 18 to 20-ish years, I think that everyone in this course probably has a decent understanding that if the bullet goes through this target, the target is going to move in the same direction as the bullet. So this is our before and after. Is this system isolated or non-isolated? Back in the previous tutorial problem, we said that a non-isolated system is characterized by usually some interaction with a wall, a ceiling, a floor, some sort of interconnected external complex system. And that's just not present here, right? We're not bouncing, we're not shooting a bullet into the wall, right? We're not saying that the target is attached to the wall. Even the target itself, it's sliding across a smooth horizontal surface. So there's not even friction involved. This is truly an isolated system. Again, mainly just because it doesn't involve doors or walls or floors, ceilings, etc. etc. Alright, so if it's an isolated system, we know from before that delta P is equal to 0. It does not change, and remember that P is a vector. What type of collision is this? Well, it's hard to say right off the bat. It's obviously not a perfectly inelastic collision, right? A perfectly inelastic collision would have the target and the bullet moving at the same speed after the collision, which is really to say that the bullet would be embedded inside the target, right? And you see that with, if you shoot a light bullet into a block, a thick block of wood. You can talk about the system then as one mega system at the end, right? It is perfectly inelastic. This is clearly not that, and it's clearly not elastic either. It's clearly not elastic because there has to be some form of deformation involved. You can't go through another object without boring a hole through it, and that boring, digging through the object, in this case a target, takes energy. It deforms the object, and that takes energy. So what type of collision is this? This is probably some sort of inelastic collision. It's inelastic collision. There's deformation, but it's not perfect. It's not a perfectly inelastic collision, right? So all we can say at this point is that delta KE, our kinetic energy, is not equal to 0. We are going to lose some amount of kinetic energy in our system here, just through the deformation. So what's the initial momentum of the system? Well, the initial momentum of the system is m1 v1I plus m2 v2I. But m2 v2I, well, v2I is 0. We have a stationary target, so I'm really just looking at 0.025 kilograms times 1200 meters per second in the I-hat direction. And what do I get? I get I get 30 kilogram meters per second in the I-hat direction. So that is our initial momentum of the system. If we look on the next page, what's the final momentum of the system? Well, just like the last tutorial problem that we did, this is an isolated system, so delta P is equal to 0, which means Pi equals Pf. Our final momentum has to be our initial momentum, which is 30 kilogram meters per second in the I-hat direction. It's simply that simple. Simply that simple. Ooh, I'm just eloquent. Man, words fail me. F, what is the speed of the target right after? I need some more coffee. Right after the bullet emerges. If we're thinking about PF is equal to 30 kilogram meters per second in the I-hat direction, it's also equal to m1 v1f plus m2 v2f. We know that our v1f 0.025 kilograms. Our v1f is 900 meters per second in the I-hat direction. And we know that m2 is 350 kilograms. So we can now start to solve for v2f. If we set all this equal to 30 kilogram meters per second in the I-hat direction. When we solve for v2f comes out as 0.021 meters per second in the I-hat direction. So if we're actually thinking about the speed of the target, it's just 0.021 meters per second. We don't need the I-hat direction or the I-hat unit vector, but it's helpful when thinking about momentum. So this is interesting. It's moving just very, very slowly. And if we think about that, I guess that makes sense because we have a huge mass compared to the tiny, tiny, tiny mass of our bullet. So now, by what percentage has the kinetic energy changed in the system? If I think about Ki is going to be just that initial bullet moving, m1 v1I squared. There's no v2I, so we can just kind of stop it there. If we have 1/2, 0.025 kilograms times 1200 meters per second squared, what do I get? I get 18,000 joules. That's a lot of energy. So Kf then is 1/2 0.025 kilograms times 900 meters per second squared, meters per second quantity squared, plus 1/2 350 kilograms times very small number 0.021 meters per second squared. What does that give me? If I plug that into my calculator, I get 10,125 joules, which is a bit less, right? It's a bit less than 18,000 joules. So if I think about the percent change, right, I can say that, Ki minus Kf, I like to take an absolute value there, divide it by Ki, right? That's going to give me a fractional change. If I really want a percent, I guess I could multiply this by 100 to get a percentage. And I find that I get 43.75% decrease in Ke through this collision. Now, I will say the percentage is a bit tricky. How we talk about it, we could talk about percent change or percent difference. These are two slightly different things, but it's the same thing from a certain point of view. I think that this is a perfectly fine way of doing it. We have a 43.75% decrease in kinetic energy from initial to final. So that is number 53. If you have any questions, pop into an office hour. Come talk to me in my email. That's fine as well. And otherwise, I will see you next time. Thanks.